Okay, we're back, and now we are going to quickly find the volume of every single thing that you ever wanted to find the volume of. Well, I could proceed like we did with area, sort of axiomatically with the most simple possible object, and the most simple possible object in this case is a cube, and specifically a cube with side length 1. And so, well, maybe I'll do this. Here is a cube, and if this is a 1 by 1 by 1 cube, then the volume of this should be 1 cubic unit. That is kind of built into the definition of volume, I would say. And we could proceed sort of axiomatically from this to introduce some kind of partition principle and congruence principle. Okay, but let's sort of skip that, and maybe let's just go right for something a little more intuitive. Well, the volume of a box. So let's say I have a box which is 2 by 3 by 5 or something like that. No, let's do just 3 by 4 by 5. That seems good. Okay, well, let's see. Can I draw this? I think I can. Here we have the bottom. All right, and let's say that this is 3. And I'm a terrible artist, so this is not going to look good. My attempt at perspective here. So this is the floor of the box of this right rectangular prism, and of course the base of the box has area 15 because these are just all squares. But then the thing is also 4 units high, and so how do I do this? Practice this in advance, maybe. If this is 4 units high, well then what we're actually going to do, maybe I'll just talk about it. What we're going to do is we're going to lay 15 unit cubes along the floor of this box, and that will produce a figure which has volume 15. And that will be 1 layer, but of course the thing is 4 high, and so there'll be 4 of these layers. And what we'll then find is that if there's 15 cubes in each layer, and we multiply by the 4 layers, then we get 60. All right, so the volume of a box is length times width times height. All right, so just taking that as something that we just understand, this idea of building a layer and then multiplying by the height, then we can find the volume of any prism. And a prism is just the shape that you get when you take a polygon and you translate that region to a parallel plane. And so perhaps we have a hexagon or something, and if I draw or try to draw a hexagonal prism, something like that. That's terrible. What is the volume of this hexagonal prism? Well, I claim that it is sufficient to find the area of the base, which is basically like the volume of something which of a hexagon of height 1, and then multiply it by the height of that hexagon. And this works for any kind of prism. And so we have sort of this formula which says the volume of a prism is just the area of the base times the height. Okay, cool. And then this works equally well for cylinders. And, well, what is a cylinder? A cylinder is just a prism with whose base is a circle. And if we know how to find the area of a circle, and we do, then if this cylinder has radius r and height h, the volume of this thing is, well, again, it's just going to be b times h. It's pi r squared h. All right, and in fact, fancy people will just call all of these cylinders. And this just happens to be a cylinder whose base is a hexagon. So you might even just start there, actually, as a kind of an axiom of volume, that any cylinder is going to have formula volume equals base times height. All right, so that's like boring. Let's get to the real deal. The real deal is pyramids. Pyramids require now some actual conversation. So how do we find the volume of a pyramid? This seems hard. Let's start with a simple kind of pyramid, a square pyramid. Again, this attempt to draw this will fail, I think. There's a particular kind of square pyramid which is particularly nice, and that's one in which the vertex is above one of the vertices of the square. Do you see that? Actually, that looks pretty good. Let's even just say that the side of this square is S, and maybe say that the height of that thing is also S. Well, what I would like to argue, and this is kind of a way of thinking about pyramids maybe for the first time, what I'm going to argue right now is that the volume of this square pyramid with height the same as the side length of the square base is 1/3 of the volume of the corresponding cube of side length S. Picture not to scale. All right, for this it's maybe best to not look at my terrible artwork and instead to look at a model. Never done this before, but this is a handheld camera. Here I have just printed this off of the internet and printed out on colored paper. And what we see is this exact thing I was talking about. This is a cube, and we can kind of see that this cube seems to be composed of 3 objects. And if we take these objects apart, we see, okay, each of them is a pyramid, a square pyramid. And the height is also the same. And so there is this decomposition of a cube into these 3 square pyramids, and thus each of them must be 1/3. All right, so that's pretty exciting. And it doesn't stop there. We don't have to use square pyramids. We could use any kind of pyramids. Again, starting with the cube as something that we seem to understand really well, this is a more complex figure. This is a cube which has been decomposed into 6 triangular pyramids. And each of the bases of the pyramids are right triangles which are half of a square. And so you can sort of see this. I don't know, is it worth it to take this apart? Maybe it will be hard to do so because I taped it so well. Let's see. If I just pull, what happens? Yeah, here we go. Here's one. They're coming apart now. Here is one of these triangular pyramids. And yeah, anyway, there are 5 more of them. Together they make a cube. All right, this seems to suggest very strongly that the volume of a pyramid is 1/3 of the volume of the corresponding prism. And in fact that's true. And before I look at yet another model of this, maybe now is a good time to talk about this subject which comes up when one discusses volume, and that is this thing called Cavalieri's principle. All right. What Cavalieri's principle says is, well, here's what, probably saying his name wrong a little bit too, Cavalieri, something like that. I think I'm spelling his name right. What this says is that, well, maybe we just start with an example. So suppose I have some square pyramid, and again, maybe I'll start with the vertex above one of the, with the vertex of the pyramid above one of the vertices of the base. Well, I claim that if I move this vertex of the pyramid about in a plane which is perpendicular to the base of the pyramid, then the volume doesn't change. Why is that true? Well, the idea is that, so here is this same square, or it's supposed to be, and now ultimately what I'm going to do is to put the vertex in the same place, but equally high off of the ground. Why do we feel that these figures have the same volume? Well, the idea is, first of all, their bases have the same area. And if and now we get to the actual Cavalieri's principle, well, not quite yet actually. What I'm now going to do is I'm going to pass a plane through these prisms at a certain height off the ground. And it can be proven, but I'm not going to do it, that when I do so, here comes terrible picture again, I don't know. When I do so, these squares that I get have equal area. And since this can be done, this is calculus basically, I can prove that this happens. And since this same thing holds at any height, well, in fact, what we're going to do is we're going to think of the volume of this figure as composed of a either large, or perhaps if you want to be awesome, infinite number of very thin slices. And to the extent that all of these slices are all congruent to each other, and that they have the same thickness, then the entire figures that they compose must have this, or that they constitute must have the same volume. Okay, and in fact, here I started with figures with congruent bases, but it is possible to start with two pyramids of arbitrary shaped base, as long as the areas of the bases are the same. An argument can be made that if you go up a certain point up the pyramid, then the two shapes you get, while possibly not congruent, do have the same area. And if that's true, if every slice, and this is Cavalieri's principle, if every slice has the same area, if you can prove that the area of this figure equals the area of this figure, and that holds for every single slice, then it holds for the volume of the entire thing. All right, so if we believe that this is true, then this enables us to find the volume of not just prisms and pyramids that we've seen so far, but also just strange prisms in which perhaps the hexagonal bases have been like moved in some strange way to be very much not. So the idea here is, here's the ground, and this guy has been moved in an oblique fashion off from where it sort of belonged if I went directly up. So what I've drawn here is a hexagonal prism whose volume I can calculate very convincingly via these previous arguments about levels. And I claim that the volume of this prism, though it might not look like it in my picture, is the same. Okay, let's call the pyramid situation settled. What we have seen now is that the volume of any pyramid is just going to be 1/3 the area of the base times the height of that prism. Perhaps we will look at one more model, because it is pretty exciting. And that is this. And I think I can do this in about a minute. This is a model of a sort of arbitrary triangular prism. And what this model shows is that this triangular prism can be decomposed into a bunch of triangular pyramids, specifically 3 of them. So you can see how that they fit together perfectly. So this is supposed to convince you that they exhaust the prism.
Well, what's exciting about this is that these can be matched. And so these two pyramids, we can see clearly, have a base in common. And so as those bases are congruent, and as they have the same height, then by Cavalieri's principle, since their bases are congruent and their heights are congruent, the volumes of these pyramids must also be the same. So what we have now is that the pink and the yellow pyramids have the same volume. Well, what about this strange blue one? Well, it also, since they all fit together, shares a face with one of the other prisms, and you can sort of see that there. And so these two have the same base, and if we put them on the ground, we can see that they also have the same height. So by a kind of a transitive property, since these two have the same volume and those two have the same volume, then all three have the same volume. And if all three have the same volume, well then the volume of each of them must be 1/3 of the corresponding prism. And so for this particular triangular prism, which was more or less arbitrary, the volume of the pyramid is 1/3 the volume of the corresponding prism. And so that holds for this prism, which was right. By this conversation, it also holds if the prism is oblique. And since any polygonal prism can be decomposed into triangular prisms, then we've really shown this now for any pyramid. All right, I feel pretty happy about this. One thing perhaps that we should mention before we do something else is if you take the volume of a cone, well, what is a cone? A cone is just a pyramid whose base is a circle. It's a sort of a infinite gonal pyramid. Well, this is R and this is H. If I would like to find the volume of this thing, it's the same formula. It's 1/3 of the corresponding prism. So it's corresponding cylinder or prism, whatever you want to call it. So this is going to be 1/3 of the base times the height, and of course we know that the base of this is pi r squared. And there we just have the formula for the volume of a cone, the 1/3. All right, this was all relatively straightforward. It's about to get really hard, and that is because we are going to talk about the sphere. All right, how do we find the volume of a sphere? Well, it seems hard. It doesn't seem to be easily decomposable into really anything. So this is what we're going to do. What we're going to do is, instead of talking about the sphere per se, we're going to first talk about the hemisphere. And if I take a hemisphere of radius r, and okay, so it looks kind of like this, hopefully. Yeah, looking pretty good. I claim that this hemisphere has a special relationship with a cone whose base, bigger, is also r, and whose height is r. Is that good enough? It's not really good enough. Just one more time. I guess to make this a little bit bigger. See if that achieved anything. Okay, so that's R, and that's supposed to also be R. All right, and the shocking, if you've never seen this before, fact about these figures is that if you add up their areas or their volumes, what you get is the volume of the cylinder with radius r and height r. Okay, and it kind of looks right in some way, right? I mean, the hemisphere is missing some stuff on the top, and the cone sort of fills in the gap. All right, I'm going to prove this. This can be done, and it's not that hard.
It will, however, require a little bit of algebra. And it's also going to use Cavalieri's principle. And what I'm going to do is I am going to grab a slice of this thing. So let me start at some particular height from the equator. Let's call that height x. So let this blue thing be x. And I'm going to consider that same x over here and that same x over here. So at the same height off the ground, I'm going to take a slice. And when I say take a slice, what I really mean is I'm going to find the area of the circle formed by passing a plane through the hemisphere at a height x units above the equator. And the volume of that infinitely thin slice is just going to be the area of that circle. And I'll do the same thing over here, and I'll do the same thing over here. And if I can prove to you, what Cavalieri's principle says, is if I can prove that the area of this circle plus the area of this circle equals the area of this circle, then the volume of this infinitely thin slice plus the volume of this infinitely thin slice equals the volume of this infinitely thin slice. And as that holds for all the infinitely thin slices, we'll have proved this relationship. Okay, so why is this true? Well, if this is x, key insight moment here is the one thing you should do whenever you're doing circle or sphere problems is draw a radius. This being a point on the sphere, if I draw this, this is also r. And since that's r, then I can calculate this missing segment here, and that is going to be, by the Pythagorean theorem, root r squared minus x squared. All right, thus I claim that the volume of this slice is going to be pi times the radius of that circle, which is root r squared minus x squared, so pi r squared, and I'll just call this, maybe dx for this infinitely thin slice that we're taking. Okay, well, this works out kind of nicely, right? The square root goes away, and this is pi r squared minus x squared dx. Okay, looking good. How about over here? Well, this one is a little bit easier, as this is r and this is also r. This is just a 45, 45, 90 triangle. So if I go up x, then I will also go over x. So that must be x. And thus, the volume of this thing is going to be pi x squared dx. And over here, this is, again, pretty easy. Since this is just a cylinder, this is just r. And so we have that this is just pi r squared dx. And look, this is just true. It's just true that pi times r squared minus x squared dx plus pi x squared is pi r squared. This is pretty awesome. What we have just shown is that the volume of the hemisphere plus the volume of the corresponding cone equals the volume of this particular cylinder. What is the volume of this cone in total? We know how to do that now. The volume of this cone is going to be 1/3 pi r squared times the height of that cone, which is r. The volume of this cylinder is going to be just pi r squared times the height, which is also r. So, from this discussion, what we learn is that the volume of a hemisphere is just, by subtraction, 2/3 pi r squared, pi r cubed. And thus, the volume of the full sphere is double that. Pretty amazing.
Okay, volume lecture done. I promised shorter, and I so completely lied. Be back in a minute for surface area.